Hello, everyone, and welcome to TMRO. Now, before we get started with our show, Jade, what are you excited about today?
Yo, straight up, we have found water ice on the surface of the moon, our moon.
That's right, water ice confirmed. Now, Space Mike, what are you excited about today?
Oh man, SpaceX has made some really critical upgrades to get closer to the first crewed mission, and I cannot wait. It's going to be so exciting.
Oh yes, it's very pretty. And then Lisa over on the observation lounge, what are you excited about today?
Well, I have Justin Kugler from MadeInSpace to talk about on-orbit construction space robots.
Oh my gosh, we've got so much to talk about today, and this is TMRO Space Orbit 11.33.
Good morning. How's everything up in the sky? Stand by.
And welcome back. I'm Jared. I'm going to be your Capcom for the show today. And we like to start off the show with some launches because launches are very exciting. So I'm going to throw it over to our resident rocket expert, Space Mike, for the epic launch minute. So, Space Mike, are you ready to go with the launch minute?
Absolutely. Let's take it away. We had 2 launches this week, and both of them were amazing. First off, we have a Vega launch, an MadeInSpace Vega launch, and this launched from the Ensemble de Lancement Vega, or the Vega launch area in Corot, French Guiana. And this launched on August 22nd, 2018 at 21:20 Coordinated Universal Time. The payload for this mission was the Atmospheric Dynamics mission Aeolus Earth Observation Satellite. And the Aeolus is the first satellite with equipment capable of performing global wind observations and will provide much needed data to improve weather forecasting for the European Space Agency. Aeolus will be the first satellite capable of observing what the winds are doing on Earth from the surface of the planet into the stratosphere at 30 kilometers up. It's using an atmospheric laser Doppler instrument to do this and will communicate with the ground via X-band and S-band antennas. And something interesting is that in Greek mythology, Aeolus is the name of the ruler of the winds, so it's a very fitting name. Congratulations, MadeInSpace. But there was another launch this week. We also had the launch of a Long March 3B rocket, which had an optional YZ-1 upper stage, otherwise known as the Wangzheng or Expedition 1 upper stage. And this launched from Launch Complex 2 at the Xichang Satellite Launch Center in Sichuan Province in southern China, and launched yesterday, August 24th, 2018, at 23:52 Coordinated Universal Time. Now, the payloads for this mission are Beidou 3, numbers M11, and Beidou 3, M12. M standing for MEO, for medium Earth orbit. And the satellites for this are really cool. What they're doing is they're trying to provide a global network for their GPS system, their Beidou navigation system, Beidou meaning compass. And something I'm really excited about is we're getting a lot more information about that optional YZ upper stage, which is similar to the Russian Fregat upper stage. And just once the Beidou network completes its network, it's going to be great. And this was just the amount of launches for China this year has been amazing. So 23 launches so far for China. Great job.
Woo! And there you have it, the launch minute from Space Mike. And of course, you just said China has had its 23rd launch. What are the launch stats looking like this year?
So for the Vega launch, that actually puts the European Space Agency at 4 orbital launches so far this year in 2018. And as I said, we have 23 launches for China so far this year with that successful Long March 3B. So the tie is so close, and I cannot wait to see who ends up launching the most amount of rockets this year. But something interesting is that China's previous record for their most amount of launches was 22 launches back in 2016. So they have beaten their previous record. This year's ended up just being so exciting.
And we're not even in the 4th quarter of the year, so we're cooking along, everybody. The race is on. And what was the most exciting thing this week out of the launches that we had? What was it?
To be honest, just seeing the Vega just leap off of the pad like it does. I mean, all those different solid rockets, those missions are really amazing. And I know Carrie Ann especially loves it when we see those things just take off like that instead of the nice slow acceleration like you see with a lot of liquid rockets. So to be honest, just because it was beautiful footage, and I love seeing it take off like that.
Yeah, solids, they really give you a good kick. And just to kind of show you, kind of give you a perspective of it leaping off of the pad, Vega is about 30 meters tall, so it's not itty bitty, and it gets out of there very quickly. So go rewatch the launch and realize that you're watching a 30-meter tall candle leave the ground very, very quickly.
Very heavy candle.
Yes, a very, very candle. So we're gonna go ahead and switch it on over to Jade because you talked about it earlier in the beginning of the show. So tell us about it.
So I honestly had to go through and reread the headlines because at first I was like, well, hold on, water, moon, I've heard this before, water, surface, moon, impossible. And clearly nothing is impossible. And yes, actually, we have found traces of water ice on the surface of the moon. And we actually found them towards the poles. And this is not super surprising considering it gets pretty darn cold at the poles. They basically found water, scientists found water ice in the bottoms of these craters that are in these regions, as you can see here, thanks Dota, where you see those blue dots, those are something called permanently shadowed regions. And basically because of moon's tilt, there are certain regions that really never see direct sunlight. And so what happens is water vapor actually gets trapped in like a cryogenic grave and theoretically can exist there for billions of years. And that's exactly where we found water. Who's we ask? It was data from M3 off of the Chandrayaan-1 probe that India had sent up. And M3 stands for Moon Mineralogy Mapper. And essentially it identified 3 specific signatures of water ice at the lunar surface. And so, yeah, we found water on the lunar surface, which is pretty darn exciting.
But haven't we already found lunar water on the moon?
I'm glad you asked that, Jared. Yes. In 2009, you probably remember when we crashed the Lacrosse satellite straight into the moon. No regard for how the moon felt about that. But essentially, we found subsurface water. So yeah, we found traces of water underneath the ground. But this is exciting because it's above ground, not underground like the Smiths were at one point. No, and this is really cool because basically, if the water is on the surface, then it's easier to access than having to dig through any permafrost or anything kind of tricky like that.
So where does the water on the moon come from?
I brought it there.
You did?
I'm kidding,
nice.
No. The water droplets guy. No, actually, so there's a few sources that water can come from on the moon. It can come from impacts like meteors and comets crashing in, or it can come from within the moon itself. So like I said, there is a layer of permafrost. There's ice underneath the surface of the moon. But the third option is actually kind of exciting, kind of cool. It's like a lab on the moon itself. Essentially, solar wind can come in and interact with oxygen on the surface of the moon and literally create water molecules. So that's another way that we can find water on the moon.
Whoa, that's pretty wild. And why is that important to have water on the moon? Well,
I'm sure you've all heard of the rumors of one day having a magnificent lunar base. Well, this brings us one step closer. Because if we, want actual astronauts to be on the moon, well, us humans, we need water. We get quite thirsty. But water is actually really expensive to transport from Earth to the moon. So if we can just have potable drinking water already there waiting for us, then that actually decreases the amount of load we would have to send up there. And I heard somebody mention in the chat already, well, rocket fuel. Yeah, exactly. So essentially you can take the water molecules and, separate them into hydrogen and oxygen and hey, there you go, rocket fuel.
Bam.
Yeah, and this all kind of comes back to, human exploration of the cosmos, which is a big thing that we get excited for here tomorrow. And this really does bring us one step closer.
So in our chat room, really well-named person from YouTube, sometimes I comment just because, good name, is asking, do we know how much water there is? Or is it just simply a recognition by that instrument that, oh, there's water there?
Exactly. So it was in trace amounts. It's not like we found giant glaciers. But from what I understand, there still needs to be additional analysis of that data. But for now, we did find traces of it, which is exciting because that could mean that, hey, maybe there's more than we thought there is.
Cool. And Vax Headroom, our resident Moona bomber here, who actually worked on the Aeolus mission, says that the LADI satellite, which was in orbit around the moon from 2013, says that they found water everywhere on the moon and helped us understand and create the lunar hydrology theories. So some very interesting stuff. So those 3 ideas that you had that came through, that sort of was supported by the data that came from M3.
And it's also kind of exciting too, because I mean, you think of the moon, the prevailing theory is that the moon was once a part of us, a part of Earth. Something smashed into us and boom, we have a moon. It didn't exactly happen like that. But the fact that the moon was once, a part of Earth, it would make sense that, hey, we'd find water there. Because I don't know if you noticed, but there's water everywhere here on this planet.
Yeah, and it seems that everywhere we're looking, there actually is like some form of water there, like either water vapor or water ice.
It's very moist.
So, like even on Mercury, there's apparently water ice there in the poles. So, wowza, that's very, very cool. So thanks for that very moist story there.
Anytime.
And now, Space Mike, you have got some very exciting updates for us, and I'm just gonna kind of let you roll with this because you were already getting very excited at the beginning of the show, and I know that when you get excited, it's just we put the quarters in and we let you run. So Space Mike, just have a go.
Feel free to interrupt me at any time if I get a little carried away, but I was so excited for this because over last week on the launch pad that sent humanity to the moon and launched 85 out of the 135 shuttle missions has been upgraded. It has had the new SpaceX Crew Access Arm installed to enable the pad to be returned to a human-rated status.
Wow.
And oh my gosh, this thing looks so futuristic. Oh man. And one of the reasons why I'm so excited about this is because even though there's been delays in the uncrewed and crewed flights of the Dragon, SpaceX is moving ahead with all the different reconfiguring of the launch pad over the next few months to return it to that human-rated status. And I did also want to share, there are some views of the tower from our community member, Loopy, known as a Wild Loopy Dragon on Twitter, who, by the way, Loopy is just a great resource. Thank you so much for submitting these photos. So there's a couple of different views of the Crew Access Arm as it's installed there, and that is just... oh man, I'm so excited for this because this is the Crew Access Arm that Dragon riders are going to cross in order to ingress or enter into the Crew Dragon. And after this, the next task is going to be the installation of the slide wire escape system should the need to evacuate Dragon quickly arise during pre-launch operations. So, this is really cool.
And also, tell us a little bit, too, about how this relates to load and go, which is a new type of rocket fueling procedure that NASA's approved. What is, first of all, can you explain load and go and then how sort of all of this is relating to that?
Absolutely. So this proposal that NASA has approved from SpaceX is actually something that they've been doing for a while now with the way that they load the Falcon 9 prior to their satellite launches, which is loading the fuel just in the last hour of the countdown instead of hours before and letting the fuel boil off and just kind of, top it off as they're waiting for the launch to happen. And it actually turns out that this might actually be a little bit safer. The whole reason for this is because of the super chill densified propellant at the Falcon rocket. And if that propellant, it needs to be loaded at the last second because as it warms up, that'll bleed off and it'll reduce the amount of thrust that the rocket can perform. So this is actually is really helpful to make sure that they get the most amount of thrust out of this. And the way that it's safer is that as they're loading the vehicle, ground crews are actually going to be far away from the launch pad when they actually are doing the fueling. And if anything does go wrong, the abort thrusters, the Super Draco thrusters on the Crew Dragon are going to be activated and primed so that just in case anything happens, they will be fast enough and powerful enough to push the capsule and its crew safely away from the rocket if there was an explosion. So even though there was a lot of kind of controversy over this as to whether or not this would be a safe procedure, turns out this would actually be safer. So I'm really happy that this has been approved and that these milestones have been met and that SpaceX is getting ever closer to their missions. The uncrewed demo flight of the Crew Dragon is going to be happening in November of this year. That's at least the soonest that it's scheduled for, no earlier than November. And then right now, the crewed mission, the Demo 2 mission with NASA astronauts Doug Hurley and Bob Behnken, is scheduled for April of 2019 for a flight to the International Space Station. So it's getting so close. We've been waiting for this for a long time, and it's about to happen. So I am So happy about this.
Yeah, I mean, I was just literally thinking back to like commercial cargo started like when I was still in high school, and like here we are now. Finally getting this ready to go. We do have some comments and questions from the chat room just to kind of highlight these. Smokey Durg says that the arm looks like something from 1980s Disney. So I would agree with that. Darknaze says that it looks so 2001. And by the way, I'm thinking that these things look cool from SpaceX, that's kind of no accident, if you will, from that. Stormer in our chat room is asking, does it retract or swing? So does it pull backwards or does it swing over to the side? Which one does it do?
It's going to swing over to the side. It's not going to retract. It's going to swing over to the side. So for the next couple of missions that they're going to be doing there, even with the uncrewed demo flight in November, there's no need for the crew access arm. So yeah, that's just going to be swung over to the side so that it's not in the way during the launch. And even for a crewed launch, that's how it would happen. As right before the countdown, the crew arm will swing away after they're all loaded and everything like that.
Yeah, just like shuttle on 39A. You know, the crew access arm stayed there until maybe, I think it was what, like 10 minutes before launch, then it would swing out of the way and have it out of the way. Therion also wants to...
Something interesting about this, too, is that it's actually, if you look at the old arms on this pad for the space shuttle, the crew access arm was quite a bit lower than this, and where the crew access arm is now for the SpaceX crew access arm is where one of the fueling arms were that kind of reached onto the top of the orange tank of the space shuttle. So it's about that same height, just for reference.
There you go, self-loading payload. What do you know? And then Therion also wants to ask, will they have an emergency cableway as well? So, jumping in a basket and riding the basket down in case things go wrong.
And that's why I was mentioning that's the next task, is to install the wire and the basket for that. So not exactly sure what that's going to look like, if it's going to be more like a hot air balloon or if it's going to be kind of like the system that you just strap into that ULA has for the pad for Starliner.
All right, very, very cool. Well, thank you, Space Mike. That was fully informative, and I now know everything about 39A that there is to know so far. So very, very cool. So back to you, Jade, because you're going to tell us a little bit about Jupiter. We're going to go out to the outer solar system,
yes,
one of my favorite places. And you got something that's talking about Jupiter's stripes, and why should I be excited about Jupiter's stripes?
Well, okay, a few reasons. A, because you are a rocket scientist and an astronomer, so you should, I don't have to explain that to you.
Not really, so, yeah.
But for the audience, the reason you should be excited is because when we think of our solar system as a whole, some of the iconic imagery that comes up is, we have Saturn's rings, and then we have, Jupiter's stripes. And it's been something that for literally centuries, we've been able to look at and wonder, what the deuce is that? I mean, to me, it always kind of looked like a cat rolled up in a ball and, sleeping. But it's not a cat. It's not furry, although that'd be kind of cool. Essentially, Jupiter's stripes are these really, really interesting weather patterns. And if you've been keeping up with the Juno mission, Juno recently sent back data that told us exactly how far these storms or these weather patterns actually go down into Jupiter. We found out that they extend about 3,000 kilometers deep, which is only about not even 5% of Jupiter's radius. So they go down relatively far, but then what we found is that they just stop abruptly. Like, they don't go down and then kind of transition into gaseous hydrogen. They just kind of bam, like a wall. So if you see this lovely image here, this kind of shows you a rough layout of what Jupiter's interior looks like. You have those clouds, which are those stripes. Those clouds then turn into gaseous hydrogen, liquid hydrogen, metallic hydrogen. I'll explain what that is later. And then potentially a solid core. So what scientists Naveed Constantinou and Jeffrey Parker did was they actually wanted to find out, well, why does it stop so abruptly instead of just transitioning, very gradually? And what they did was they deduced a mathematical model that actually explains why. And the answer, folks, is magnetism.
Oh, snap.
You see? So what they did is, again, they devised a mathematical model, and they actually used data from our own jet streams and weather patterns here on Earth, and they were able to actually explain that the storms only go down so far, and they stop at a point where we think the hydrogen of Jupiter becomes something called metallic hydrogen. And essentially what that means is if you look at Jupiter, it's made mostly of hydrogen and helium, but it's massive. And hydrogen does creepy things on Jupiter that it does not do on Earth, in that there's so much pressure compressing these hydrogen atoms that the electrons literally get squeezed out. You have this like kind of juicy electron soup.
So basically the electrons can move like they can move through a metal.
Precisely.
Exactly.
It becomes conducive, and you have electricity, and you have magnetic fields.
That's cool.
And so that starts to happen right about where the stripes stop. And is that a coincidence? Maybe not. Probably not. Huh. So we think that the magnetism is actually what's stopping, because based on data we've actually already kind of studied here on Earth, magnetism tends to halt jet streams like that.
Gotcha. So that's how we know that the magnetism influences Jupiter's jet streams.
Exactly.
Based on the models that we've done.
Exactly. So this is kind of a really exciting intersection between theory and observation.
Do we still have a good idea of what causes weather on Jupiter yet?
Well, yeah, of course. So basically, when you're looking at Jupiter and you see those bands and zones, what you're seeing is all of those reddish colors are ammonia, and those stripes are basically caused by jet streams on Jupiter. The reason why it has those fancy jet streams and those beautiful patterns is because, unlike Earth, there's nothing physical obstructing those winds. So you get rather smooth, very defined lines. Versus on Earth, again, we have those pesky mountains, and we're a very lumpy planet. But yeah, essentially, that's what happened. And again, it's pretty exciting because we had found this data, and what the scientists actually did was they were able to match kind of like a theoretical prediction with the data that they actually saw.
Whoa, that's when you know you're doing very good.
Exactly.
As a scientist. So what's the point? So what's the point of this?
Well, I'm glad you asked.
Because that's happening to Jupiter. So
I know,
what's
right?
the point of it here on Earth?
Well, I'll tell you why you should care. The vast number of exoplanets we find happen to be Jovian-like in that they're gas giants, and a lot of them are what we call hot Jupiters. So hot Jupiters, so hot gassy giants. Sounds like a few of my brothers, but essentially. This is exciting because, again, if we're looking at habitability and we're looking for potential life sources in exoplanets, then being able to understand our own gas giant in our backyard would help us to better understand those farther out. And I mean, even without having to use habitability as an excuse to study, Jupiter, it's knowledge for knowledge's sake. Again, it's always really cool when your theory lines up with what you see. I mean, look at Einstein. He had all those great theories, and then hey, even today we're still finding out that hey, he was correct.
Yeah.
So I mean, just discovery and knowledge for knowledge's sake.
Yeah. Interesting. Very, very cool.
Blows my mind, though. I've always just assumed that the storms went hundreds of kilometers in, and this blows my mind that it's only 5 kilometers. Is that what you said? That's how far the storms go before they stop?
No. The storms themselves, 3,000 kilometers.
3,000.
Yeah, which I mean, relative to the entirety of
right. Way less than I thought.
That is amazing. So we do have some questions from the chat room to kind of bring it from people. Henny's Warwarp on Twitch is asking, how fluid would the hydrogen be at these pressures? And if I recall, it's basically like, that's your answer.
Exactly.
Nobody, and it kind of leads into Space Kyle's question from our chat room as well, which is, have we ever made metallic hydrogen on Earth, or are the pressures and temperatures too extreme?
I'm excited you asked that,
yes.
Space Kyle, because we have actually been able in labs to somewhat do that to hydrogen, but only very small amounts at very, very short amounts of time. Not very long enough to do anything too substantial when it comes to studying it, and that's why Jupiter has always been pretty fascinating in terms of like a physicist standpoint, is because, well, literally it's doing things to hydrogen that we can't really dream of doing here.
Yeah.
Yet.
Yeah, if I remember, in the 90s, they were working at Harvard to do it, and they were using an instrument called a high-pressure diamond anvil cell, which is literally an anvil that squeezes 2 diamonds together in order to generate over 1 million atmospheres of pressure. And then they would fire a laser into that as well to get it up to nearly 3,000 Kelvin in order to work with that as well. So,
that is dumb hot.
That is like, holy smokes. Awesome. So, slightly difficult to work with that.
A little bit.
just a bit.
I mean,
but there you go. There's a that is such a cool story that they were able to. They literally modeled it and then confirmed it.
Exactly.
So very, very cool. Yeah. Woohoo! Now, speaking of yay, we'd like to say yay to our escape velocity citizens that help us out here on the show. Now, they give us $10 per episode. They make the show happen. Thank you for supporting us. There's many ways to help the show. You don't have to necessarily, give us money in order to make the show works. You can subscribe. Don't forget to choose to ring the bell as well on YouTube. You can go to community.tomorrow.tv. We're always looking for help there as well. And if you'd like to financially help us, you could also head over to patreon.com/TMRO to help us out as well. So we're going to take a quick little break, and when we're back, we've got Lisa on the observation deck. We're going to be talking to MadeInSpace, and I'm very excited to hear what they have to say. So stay tuned. There's more tomorrow right after this.
Look into her face, determination in her eyes. She won't give up or quit or fall for little fashion lies. Filled with awesome expectation, this girl's a fascination. And nothing in her way will keep her from her destination. Cause she's fire walking, she's fire walking. When it's hot, she keeps on moving. Through the heat, keeps on improving. Yeah, she's fire walking, she's fire walking to be free.
And thanks for sticking with us. My name's Lisa, and I have Justin Kugler here from MadeInSpace to tell us about some really, really cool stuff. So first of all, Justin, thank you very much for taking time out of your Saturday to be with us.
Thank you. I'm very happy to be here.
My first question for you is, could you tell us a little bit about your role at MadeInSpace and why the company even exists?
Sure. So I'm our business development director for advanced projects, which means not only do I go, find new business for the company, it's my job to help go find all the new blue sky projects that we do, build new strategic relationships, and really help people understand how to use our technology and how to put it to work. And that's really what we're all about is, moving the means of production from Earth into space so we can create new missions, new business opportunities, and industrialize from low Earth orbit out to the other planets and really bring space into our economic and science and social sphere.
That's so cool. So you guys have this whole plan of, we can't just go straight from what we have today to constructing giant structures in space. There has to be steps along the way. So what were the first steps that MadeInSpace took to enable this, on-orbit construction future?
Sure. So when our founders got together through the Singularity University Graduate Studies Program, and when they looked at the state of the space industry, they saw there were a lot of people trying to do really interesting and really exciting things with launch. And there are a lot of people trying to do really interesting and really exciting things with small satellites and CubeSats and things like that. But they noticed that there really wasn't a whole lot of activity going on with in-space manufacturing. People had tried to do that in the past. There were, giant constructors that were intended to be flown in the space shuttle payload bay. And, back in the 70s and 80s, there was a vision that the space station itself would become a massive construction platform for deep space missions. But it turns out that if you try to apply conventional manufacturing techniques in space, they don't all work exactly the way that we think that they would. So our founders decided, how about start with a clean slate and look at what is the state of manufacturing technology today, what is adaptable to the microgravity environment, and then how can we build on that to expand those capabilities over time. So they started by putting the first 3D printer on board the space station. It's based on a fused deposition modeling process, which you see in 3D printers all over the world today. But we learned that gravity actually does a lot of the work for 3D printers on the ground. So we had to devise an entirely new control and deposition mechanism so that you get a very precise layer build every single time. And we refine that process enough so that you can run a printer on the ground, run a printer on the space station, and run a printer through the entire +2, -2G parabola on a parabolic flight and you can't tell the difference between the three.
Wow, that's incredible. So you guys sent a 3D printer up to the International Space Station. Is that the only equipment that you guys sent up there, or was that part of like a larger project?
Certainly. So the first 3D printer that we flew in 2014 was a NASA-sponsored tech demo where we did a ton of characterization work with our partners at NASA Marshall Space Flight Center, really getting the science and the process behind doing 3D printing in space down to a science instead of an art. And based on those lessons learned, we then flew our second generation printer, the additive manufacturing facility, to the space station in 2016. And that is a fully self-contained facility. It fits in an express rack locker on the station. It's entirely self-contained. All the astronauts ever have to do is, occasionally change out feedstock cartridges and take printer pieces out when they're done. Otherwise, we run it all from the ground. We can run multiple different materials in it. And we own and operate it as a commercial facility through the ISS National Laboratory. So whenever NASA wants to use it, they issue us a task order, and we provide manufacturing as a service. And then if there are other customers, non-NASA customers, that are interested in utilizing that capability, they can then give us contracts just like they would Shapeways or some other terrestrial company to provide that same service. We just happen to do it on a platform that's moving at about 18,000 miles an hour and is in constant freefall.
There must have been a lot of challenges, I guess, associated with 3D printing in space. You guys seem to have nailed it so far because you're continuously improving and sending bigger manufacturing equipment up to the ISS. But what were some of those kind of challenges that you guys had with the zero-G environment?
Well, one of the biggest challenges is that when you're calibrating a manufacturing machine here on the ground, you do have people in the loop, hands-on right there. So if you identify a problem, it's fairly easy to fix it, adapt it, and get it back into production. But just by virtue of the nature of the flight cycles to and from station, and that we're having to do remote operations with an amazing group of astronauts who may not have even seen the briefing on how to operate the printer until they get to the space station, and having to do all the internal operations remotely, troubleshooting can actually be fairly time-consuming. That's why we spend a lot of time working with our hardware on the ground, making sure we understand all the ins and outs of it, and automating as much of the process as we can so that we can minimize that troubleshooting process on board. And in the process of learning those lessons with the first printer, and that we've since applied to our AMF and other new payloads that we're flying to the space station, we've learned to make it as user-friendly as possible. So, for example, we design things so that an astronaut only has to use one hand to change things out because, on the ground, you're letting gravity do a lot of the work for you. You've got your 2 feet on the ground so you can use your 2 hands. Whereas up in space, since they're floating around, they have to be able to position themselves, and they may have to be holding something else like a flashlight or another piece of equipment while they're doing some kind of troubleshooting or part exchange operations. So we've designed that so that all they have to do is use their one free hand, either change print heads or do feedstock cartridges or change print trays, things like that, just to make it easier for them. And these are things that you wouldn't normally have to think about when you're doing operations on the ground.
Yeah, I didn't even think about that until you said it. But as soon as you said it, it makes complete sense. Your hands are a valuable resource in microgravity because you always have to secure yourself so you don't float away. So that's a really cool design thing that you guys have incorporated. I have another question here relating to those different challenges of printing in space. It's from our chat room, and it's from Twicked, who asks, with such a controlled environment like the ISS, like the temperature and the humidity, were those conditions perfect, or did you have any issues related to those environmental conditions on the ISS?
No, that's a great question. So with all of the hardware that we fly to the space station now, we have a built-in environmental control unit. It's in part to make sure that nothing that we do with manufacturing operations emits anything harmful to the crew. And that's my 6-year-old daughter. Hi, Ellen.
The internet says hi to Ellen
so, they have very strict requirements on what you have to do to keep the crew safe, because we don't want anything floating into their eyes. We don't want them breathing anything in. So our environmental control unit makes sure that both nothing nasty gets out into the cabin air, but it also turns out that, with the astronauts living and working and breathing and exercising, it's actually a fairly humid place in some ways. And some of our manufacturing operations, like our fiber optics manufacturing project, require ultra low humidity. So we have that ECU to also make sure that the internal manufacturing environment is exactly where we need it to be.
That's really cool. Another question kind of related to having things floating around in the printing environment comes from our chat room. It's from Avitus Nova, who asks, how do you initially secure the object and prevent it from floating around in the printer?
Another great question. So for our 3D printer on the station, AMF, we actually have print trays that act as a starter surface, and that's where we start manufacturing the part. But we have very careful manufacturing operations so that it doesn't actually adhere entirely to the print tray. It just acts as a kind of temporary tacky surface. So that way, when the print is done, all the astronaut has to do is pull it off. But they don't actually have to, pry it off. Usually, unless we're working with something like HDPE, high density polyethylene does get kind of sticky. So we do actually have a little pry tool for the astronauts if we're printing with something in high density polyethylene.
That's really cool. You guys seem to have thought about pretty much everything related to that. So that's awesome. Another question from our chat room is from Space Kyle. So Space Kyle asks, your current printer uses plastics. Have you done any work to determine the viability of other 3D printing methods, such as using resin or metals, UV lasers, stuff like that?
Yes. So we're actually doing a lot of work on other materials right now. We have got a phase 2 small business research grant underway with NASA Marshall right now for a hybrid metal manufacturing process where we will actually generate what they call a near net shape out of a welding-based additive metal manufacturing process. And then we've actually figured out how to make CNC tools that capture their own debris. So we can make kind of a rough shape using the additive process, and then we use the subtractive process to generate any fine surface features or high tolerance sections as required. And so we're very excited to be working on that with NASA Marshall, and we hope to fly that to the space station soon. We're also doing some work on resin-based stereolithography in microgravity. We tested that out on a parabolic flight, and we're working with NASA Johnson Space Center on developing a flight version of that right now.
That's so cool. You guys are working on so much amazing stuff. If you get those new facilities up on board to the station, how does that change the way the astronauts go about their work?
Certainly. So one of the things that I really love about our process is that it is inherently modular, inherently scalable. So, right now we have systems that are built around the kind of footprint that's optimal for supporting on board the space station. So we designed to be as small, as compact, and as self-contained as possible. But we're also working with the companies that are developing the habitats for the Lunar Gateway, as well as commercial low Earth orbit facilities, to build newer systems that are optimized for long-term operations. So, and when you combine that with our multi-material manufacturing capability, that would actually give you the ability to really make just about any kind of spare or any kind of custom solution that you might need. And that's a big problem that they're trying to solve right now, because there's a lot of mass and a lot of volume taken up on the space station with all of the tools and extra parts that they think they might ever need, because you don't want to get stuck not having one. And right now, while we're in low Earth orbit and we have regular resupply to and from Earth, that's not as much of a problem. But, even with the Lunar Gateway, it's only going to be, periodically sustained. And when you start talking about Mars missions, where, you're talking about months to years between supply missions, those people are going to be effectively on their own. And so they've got to have the ability to build whatever solutions they need to solve whatever problems they encounter in real time. We won't be able to just ship something up on the next flight like we do at the space station today. So we've got a lot of effort into making sure that we have that broad suite of capabilities available. In fact, that's one of the things I'm really excited about that we're working on right now. We have a grant from Space Florida to develop a new electronics manufacturing capability in space using additive processes with our partner company called Nanodimension. And they've developed a very high resolution electronic ink method that we're working with them to adapt to the microgravity environment. And so when you combine, that precision metal manufacturing with the polymer manufacturing that we do today and some of these more advanced capabilities that we're developing, then we'll be able to really, open up the aperture on what kind of solutions we'll be able to provide on deep space and long duration missions.
That's awesome. By the way, the next question is for your daughter. Does she plan to go to space someday and work in 3D printing on the space station as well?
Okay, Ellie, this question's for you. They want to know, are you going to go to space one day and build things up on orbit?
I don't know yet.
You don't know yet? You're still thinking about it?
Mm-hmm.
Okay. She's still thinking about it. She did tell me once that space is dangerous, so I can go, but she needs to stay here and take care of her little brother.
That is adorable. My goodness. So coming back to how manufacturing electronics in space, being able to have astronauts build what they need when they go to Moon and go to Mars and beyond, one thing that's also important is utilizing the resources that you have and recycling those resources. So we have a question from the chat room, from Twitch actually, from Hannes Warwarp, who asks, can you recycle excess printing materials to reduce waste?
Yes, in fact, we are flying our first recycling machine to the space station in just a few months. We have a partnership with a company called Braskem North America. They're the hemisphere's largest producer of materials like high-density polyethylene. And they're based out of Brazil. And if you know anything about Brazil's industry, they've done tremendous things taking advantage of their natural sugarcane resource and diversifying it so that it's more renewable. And that's how they get their ethanol supply and more sustainable. Well, they've figured out how to make high-density polyethylene from the waste byproducts in their sugarcane industry. So now it's a renewable resource. Well, we've been working with them to make this high-density polyethylene fully recyclable. And so that's interesting on multiple levels. From the space perspective, high-density polyethylene is a great material for medical equipment, food-safe equipment. That's what milk jugs are made out of. And it's good for soft goods. On top of that, if we can recycle that, then that means that you've dramatically reduced the waste stream that you get from those kind of soft good and consumable activities. Braskem is interested in that because they have a vision of one day being able to have sugarcane farms on the Moon and Mars that have this 100% renewable, 100% recyclable material cycle. And then on top of that, because our technology is again modular and scalable, they're interested in adapting that for their waste streams so that we don't have so much plastic going into the oceans. Because it's very important to them that the products that they put out be used for what they need to be used for, then come back in and are reused in a significant way, so that way they're not contributing to the problem of plastic waste in landfills in the oceans. And they see our technology as helping them solve that problem.
That's awesome. I love how people are working on things for space that can actually also parallel be used on Earth and help people down here and make our world and planet better. And to tie that in with what you guys have been doing as well, you guys are working on on manufacturing fiber optics on the space station as well, I believe. Can you tell me a little bit about that and what the results of that were?
Yes. So we're very proud of our fiber optics and manufacturing project. It's still in the experimental phase. Like I mentioned before, dialing in a process on orbit is very different than dialing it in on the ground. So we've done a series of experiments over the past year, making sure that we get all of the elements of the process optimized. We hope on the next flight to actually be able to do a complete end-to-end cycle. But, like I said, it's still a developmental process, so we'll see how that goes. What, makes us excited about the fiber project is that this is a fully commercial project. We didn't ask NASA for money. We didn't ask the National Lab Management Organization CASES for money. We are actually paying for this out of our own R&D funds and a standard commercial materials development grant from Space Florida. Essentially, they're investing in that project the same way that they would invest in, say, SpaceX or Blue Origin to buy equipment for their factories here in Florida. And in doing so, we're essentially building on scientific research that was done by the Air Force and NASA that showed that there are certain classes of materials that if you make them in a microgravity environment, the imperfections that you see on terrestrial manufacturing processes go away. And this is really important for this particular class of heavy metal fluoride glasses that if you can ideal state, they have a 3 times wider transmission window than silica and up to 100 times less attenuation than silica. So that leads to better fiber optic lasers, better network connections for server farms, and eventually one day we hope to actually be able to make entire transatlantic cables with no repeaters out of this material. Now, obviously, to make thousands of kilometers of cable, we need much larger facilities than what we can fly on board the space station today. But that excites us because if we can demonstrate a minimum viable product on the facilities and infrastructure that we have today and close that business case, that creates a virtuous cycle where we can bring in more customers and build up more business and eventually have a facility of our own.
That's really cool. It seems like you guys have sorted out where you guys need to go. You've done all of your initial testing. And you're right, if you can make this business case close and you're demonstrating this tech, this leads to a much more positive space tech future regarding on-orbit construction. So what is next for you now that you guys have proven that you can print on station, you've proven that you can do fiber optics, high-quality fiber optics in space? What's the next step?
So there are 2 really big thrusts that we have at the company right now, and they're actually manifesting in a number of different projects. 2018 has really been a banner year for us. At last count, we have over 13 new start projects this year. We're growing our offices both in California and Florida. So if you want to help us build the next generation, we are hiring. It's listed on our website. But the 2 areas that we're really excited about right now are continuing this advancement of what we call microgravity-enabled materials. We have 3 new pilot projects in development there to manufacture high-quality superalloy metals, as well as to manufacture high-quality single crystal materials. So, for example, on the ground, when they make silicon wafers, it's a very expensive, very highly chemical, very high temperature process to make these large single crystals of silicon that they cut the wafers into. There's some research that suggests that we can actually make better single crystal materials in the low gravity environment on board the space station. So we're investigating that. Then the other kind of big flagship project that I'm really excited about is our Archinaut technology for in-space manufacturing and robotic assembly. A big chunk of our team is down in Southern California right now doing an entirely automated manufacturing and assembly test in the big thermal vacuum chamber where Northrop Grumman has tested the James Webb Space Telescope. This is important because what we do is take the launch shroud and the limitations of the launch environment out of the equation by fabricating structural components that are optimized for the low gravity environment from raw feedstock. We can build space structures that are much larger and much more efficient than anything that's been imagined before. So we're doing that functional demonstration here on the ground right now, and we're waiting to hear back from NASA on our first proposal to actually test that in an operational sense up on orbit. And if we get that award, which we very much hope we do, we'll be doing that demonstration in about 3 years.
So with the Archinaut program, we just watched some footage there of the Archinaut robot arms grabbing different pieces and constructing them together. It looks like autonomously. But the Archinaut program itself, it's not just one mission, right? Are there multiple steps in Archinaut? Because I have a couple of videos here from the Ulysses program and the DELO program. What are the differences between those?
So the thing that really excites me about the Archinaut technology is that it truly is a platform technology. By combining extended structure additive manufacturing in space with robotic assembly and automatic integration, you can accomplish a wide variety of missions, from building trusses to building antenna segments to building interferometer booms. It really unlocks the imagination in terms of what you can do and what kinds of missions you can accomplish. And that's why we have a number of applications projects that are underway now with NASA, DARPA, and we're starting to talk with some of the large space prime integrators about how they can put our technology to work.
That's awesome. And so what kind of structures will the Archinaut program be capable of building on orbit?
So, at its kind of simplest form, with the extended structure manufacturing device itself, you can make, very large, very efficient booms. For example, the test machine that we built through our Phase 1 project with NASA, we built a 37.7 meter long continuous boom, really just to see how far we could push it. My daughter's playing with lights, sorry.
She's adorable.
That's important because before, the world record for the longest continuous 3D printed object was about 5 meters. We're now certified by Guinness as having the largest 3D printed continuous object in the world. So we made a boom that's about 7 meters longer than that Vega rocket that you showed earlier, which it's actually stuck in the building now. NASA wouldn't let us knock any of the walls out to take it out of the building. So that's going to be interesting to see what happens with that. But with that kind of capability, that allows you to build ultra large structures like we showed in the Ulysses video. When you combine that with robotic assembly, like what's shown here in the DELO video, that could enable you to do things like put like a 40 meter diameter radar reflector or communications reflector on a satellite the size of the Laddie mission. And that's important because right now, a lot of what's limiting what we can do with small satellites is, the size of the antennas that they can carry. So if you can fly, smaller, less expensive satellites at lower altitudes, but have antennas that are large enough to handle, high density video and other high throughput services, that allows you to dramatically increase the capability of your satellite networks.
I think what you guys are doing with on-orbit construction and the steps in your program that you guys are doing are just so incredible. Of course, it hasn't, the Archinaut stuff hasn't, oh my God, this is the best interview I've ever done. This is great, so much fun. The cool thing is also that when the lights go down, we can still see you, so your camera must be really great.
That's good. Yeah, my daughter's trying to put a Starfield background for me.
Oh, that's so cute. Oh my goodness. When she's a little bit older, if she wants to come and help us here at Tomorrow, we would love to get her on and get her interviewing people someday. I think it'd be really cool. She seems to love being on camera, so that's a great trait. So Archinaut hasn't flown yet, though. So this is all going to be great, but we need to make sure it works. So how confident are you guys that you can actually pull this off?
Oh, we're supremely confident. We've actually already done some ground demos of the particular architecture that we've proposed for that first flight demo. And we have a strategic partnership with Northrop Grumman Aerospace Services and Northrop Grumman Technical Services that has really underpinned a lot of what we're doing. So they focus on, spacecraft avionics and a lot of the complicated spacecraft integration, so that we focus on what we do best, and that's the on-orbit manufacturing and robotic assembly piece of that. And so as we're developing those systems, they're teaching us how to operate long-term in a space environment and build on that storied history that they have, so that we don't have to make all of the same lessons that they've already learned with decades of experience in this business. And they're sticking with us in this phase 2 effort that we've proposed. They're a big part of our team, and we're very excited to continue that partnership going forward. And I think that's something I would like to mention. I think it's been really important to our success is that we're a small, roughly 50-person company that has grown tremendously, especially over the past 3 years since we first started flying equipment to the space station. But we are also, I think, humble enough to know that we don't know what we don't know, and we need good partners and we need good teammates to deliver advanced missions and the advanced capabilities to the people that actually need them. And so we've built these great partnerships with companies like Northrop Grumman, Brascom. We're doing a lot of work with Moog CSA Engineering on adapting our technology to use on ESPA rings, and they've been fantastic partners on that. And so I think that's been a key element of our success is building the right teams and the right partners in industry to show to people that we can deliver really amazing capabilities.
And if people wanted to find out more information about MadeInSpace, where can they go?
So our website, MadeInSpace.us, is a great place to go. It's where we post a lot of our updates on new projects and some of our new R&D. We also put all of the videos that we've shown online on our YouTube channel. So if you just search for MadeInSpace on YouTube, you'll find our channel. And then for current events and news, go find at MadeInSpace on Twitter and MadeInSpace on Facebook. And that's where we keep everybody up to date on what we're doing.
Awesome. Well, you know what? I wish you guys all the best because you're doing amazing work, and I think this can really revolutionize the way we as a civilization go to space. So thank you very much for your time, Justin. And before we go to break, I do want to give a very big thank you to all of the citizens of tomorrow, because this show would not be possible without your help. So these are our Escape Velocity citizens. They contribute $10 or more per episode, but we also have our orbital citizens. And our orbital citizens contribute $5 per episode. They get their name in the show as well as a bunch of other cool rewards as well. So if you would like to contribute to the shows of tomorrow, head over to patreon.com/TMRO. All right, we're going to take a quick break, and when we come back, questions and comments from you, the community of tomorrow. Stay tuned. We'll be right back.
Science. It both draws us together and tears us apart, brings discoveries to cure us and threaten us. It is neither good nor evil. It is what we decide to make of it. There is so much more to learn, and we are curious. Together, let's explore the science of tomorrow.
And welcome back. We're so glad to have you back for the final segment of our show, which is where we get your comments from last week's show. And we had a pretty cool show last week, I gotta say. which was about achieving big things with small sats. We had Emery Stagmer, who's here today, our resident Moona bomber, Vax Headroom, and Craig Elder on to talk about small sats, and you guys had a lot of very interesting things to say. So we're going to go ahead and get started with our first comment off of YouTube by Alejandro Alcantarilla, which is just a note. Velocity and position are always relative to something, so saying X probe is the fastest ever doesn't really mean anything. Parker Solar Probe will be the fastest probe to orbit the sun, a velocity relative to the sun. New Horizons was the fastest one to escape Earth, and Voyager is the fastest one to escape the solar system. And I did grab some stats for you guys, just to let you know some things, which is that New Horizons was the one that left the Earth the fastest. It was moving 58,500 kilometers an hour at third stage burnout, which is about 16.25 kilometers per second. So it was cooking at that point. And then Voyager 1 is currently exiting the solar system. I looked it up just a couple hours ago on NASA's website. They estimate that it's currently moving at 61,198 kilometers an hour, just a hair under 17 kilometers per second. So, wow.
That's really fast.
That's cooking. And just to sort of remind everybody that Parker Solar Probe will be the fastest object we've ever sent into the solar system in terms of relative velocity to the sun, which it will reach nearly just about 200 kilometers per second when it is at its closest approach to the sun in 2024, which is ridiculous.
I want to know how fast the SpaceX Roadster is going right now.
Oh,
can you track that?
I'm sure you could somewhere.
Yeah.
So that's definitely the fastest car in the solar system right now. So yeah, I guess if we're gonna pull that up, we can figure out how many kilometers per second it is. Actually,
I think that's a real website.
What you got, Mike?
Oh, while we're waiting for that, we should move on to the next one. And if we find that, we can
yeah, sure thing. That. All right, and our next one actually comes from the community of Tomorrow. That's right. We got this one from Frida from community.tomorrow.tv, which is, I know a college student who did CubeSat design as a senior project. CubeSats include onboard permanent magnets, which quickly align the CubeSat with the magnetic field of the Earth. So when we see the CubeSats flailing about and rotating after a cosmonaut manually throwing it out, don't worry, it will quickly stop rotating and settle down into a happy orientation.
Unless that CubeSat that has a magnet also is next to a CubeSat with another magnet, as we learned last week from Vax. They can like magnet together. And then, you know,
whoops.
It's bad.
Whoops. Unintended match made in space.
So, Mike, what were you going to say?
Well, hopefully, I guess, yeah, I can see how that could still happen. But I mean, that's brilliant though, to have a passive system like that that can just orient itself with the Earth's magnetic field. That blows my mind. So yeah, that's really cool.
Yeah, very, very neat. All right.
How neat is that?
Yeah, that's pretty neat. Moving on to our next comment from Michael Farrell off of YouTube, which is nano-engineered swarm bots seem to offer an efficient way to do relatively cheap planetary exploration relating to the small sat concept. So small satellites, maybe the future of planetary exploration. So, I mean, we were just talking about additive manufacturing in space.
Exactly.
So why not literally just print a whole bunch of CubeSats on board of whatever you got and then, you know, have your cosmonaut chuck them overboard and then they use their own little propulsion system to go off somewhere.
That would be cool.
That sounds adorable.
There are a lot of companies working on CubeSat propulsion. So a lot of them use water as the fuel, which is, you were talking about water on the moon, so throwback.
There you go. Way back when.
So if we use these resources that are around the solar system, like load up your CubeSats, you're good to go.
Exactly.
Yeah, and
I mean, the idea
ahead,
having
Mike.
like a bunch of swarms, it's redundancy. If you send up 100 spacecraft to do a mission and only 20 of them succeed, at least you still had 20 of them work instead of sending up one that doesn't work. So I really like those ideas, like from the Starshot initiative, or even the CubeSats that are coming out of Cornell University. That just chipsats, as they're calling them, just swarming these things out, and even if just a couple of work, can be experiment as a success. So.
Yeah, I really love the idea. Honey's Vorwerp basically took the words right out of my mouth from Twitch, which is maybe each group of small bots could have different sensors. Just throw a flotilla of CubeSats at Neptune. Yeah, I was joking the other day with a friend that we should just basically get a Falcon Heavy of CubeSats and launch it at something.
Oh my goodness.
But really, that would work out pretty well, because you could have different instruments measuring different things at different altitudes as you go past Mars, or wherever you may be targeting with that. So it's almost like this birdshot blast going out there.
And if you shot them at Mars, and say you had two CubeSats that were kind of away from each other, looking at the same thing, could you use that to work out the height of features and stuff?
Yeah.
Because they're different angles?
You absolutely should be able to. That's correct. And then, and then we'll have a big cloud of debris as well out in the solar system for someone to run into
That was
later
going to be one
well.
of my questions, because I understand the argument of quantity, and the more you send, the more likely at least a portion of them will be successful. Are they so small that the amount of pollution would be negligible in our solar system, or is it to the point? Do you think it would get to the point where it's there are just so many of these darn little rascals everywhere, and they're not exactly falling into planets or anything?
I think if you look at how big the solar system is compared to a CubeSat, just chucking one out into the solar system is not as relatively dangerous as having it in orbit around the Earth.
Absolutely.
So,
I can see that.
Yeah. So, but also I would like to see some sort of mitigation.
You'd think so, because think about it on a commercial, scalability. So let's say there's a commercial company that's oh, well, I'm going to manufacture 1 million CubeSats so that I can have even more accuracy or even more success rate. And then once you start to get into that exponential, we'll chuck 2 million. I know this is getting ahead of myself, but I just...
Sure.
Yeah, we might have a problem.
A little bit.
Yeah.
But
just
still,
a bit.
It's fine if you're doing that for low Earth orbit, because those things will deorbit just through drag over 1 to 3 months. But if you're sending these things out into the solar system, that's a whole nother ball of wax right there. So yeah, if you're sending out hundreds, thousands, millions of these things, then yeah, you are contributing to debris fields, so to speak, that could become a problem for our future. But
and not just around our
what
planet
Jared's
now.
talking about, there's so many objects out there already, that are minuscule that we don't even know about that yet. That we would be contributing to with that sort of case. So, the danger's kind of already there, I guess, if we're worried about future spacecraft crashing into these things. But I agree with all of you. We should have some sort of mitigation for those type of experiments. But since we're only going to be launching the first CubeSats to the lunar system, hopefully next year, we'll get a lot more information about that type of thing. Just that distance and how we can mitigate those ones. What's their end of life scenario?
Yeah, very interesting. Good discussion. Maybe that might be something I could see a roundtable topic or an ISDC panel about that at some point. So, moving on to our final comment from Greg Woods from YouTube, which is a correction, apparently, for last week's show about a story, which is white dwarf stars are not cool. Red dwarf stars are cool. And indeed, looking it up, red dwarf stars, they have surface temperatures at just a little bit about 3,800 to 4,000 degrees Celsius, while white dwarf stars, at least right after the end of that star's life that leaves a white dwarf around, they're usually at about 100,000 degrees Celsius.
Pretty spicy.
They do cool down.
Eventually.
It does take a very long time for them to cool down. No white dwarf star that has been made so far in the universe has cooled down enough to basically become what we would call a black dwarf, which is not emanating any radiation beyond background with it. But hey, If you know, it's as I've always said on the show, we have a very smart audience watching us, a very good audience watching us, and if we ever get something wrong, our audience never hesitates to correct us. So, which is good.
I dig that.
Yes.
Does that mean you could run into a black dwarf unexpectedly if you can't see it?
Oh no, not again.
That was a legit question.
I would imagine that you probably could. So, but I would hope that you would be able to detect
I
that
suppose you
through
feel
other
the
means.
gravity before. Yeah.
So.
Okay. Whatever.
Yeah,
Sorry.
just to remind everybody, in astronomy, temperatures are opposite the taps that you have in your bathroom. In your bathroom, you probably have red associated with hot, blue associated with cold. It's actually opposite in astronomy. Red are the cooler objects, blue are the hotter objects. So if you ever go to your friend's house and they're an astronomer and you need to wash your hands with hot water, make sure to use the blue faucet. So. Very good stuff.
Thank goodness.
So,
I don't know what I would have done without that information.
With your permission, Capcom, I did just a quick Google search, and according to Google, the Tesla Roadster with Starman's going 3.5 kilometers per second.
okay, that sounds about right. Yeah, it's out beyond Mars's orbit, if I remember correctly, at this point. So it should be moving relatively slower than even Mars does in its orbit around the sun. So very, very cool. All right. Well, there you go, folks. The Tesla Roadster, not really moving all that fast at the moment, was moving fast when it left Earth, but I think even at 3 kilometers per second, it's still the fastest car in the solar system, at least. So very, very cool. So, to wrap up our show, we want to thank our escape velocity citizens. Of course, these folks have given us $10 or more per episode. We also have our orbital citizens. These folks have given us $5 or more per episode. We also have our suborbital citizens, which give us $2.50 an episode or more. And of course, our ground support citizens, these folks give us anywhere from $1 to $2.49. That's very exacting. Over on patreon.com/TMRO. We cannot do this show without these incredible folks who help crowdfund the shows of tomorrow. It is so amazing that all of you are willing to financially help us out as much as you do, and we cannot express our appreciation. We cannot quantify it enough to let you know how much we absolutely adore you, and maybe we love you a little bit as well. So
This is getting very sweet.
Yes, it is.
So much.
Very intimate.
So we have got a heck of an episode next week, because we have someone who I believe, if I remember correctly, has been the guest the most actually on this show. Which is sort of our annual check-in with Dave Maston. You may have heard of a space company called MadeInSpace Systems. You know, they're just flying autonomous rockets out in the Mojave. No big deal, right? But, you know, we're very excited always when Dave Maston comes back, because basically half of the interview is Dave, Dreamy Dave, basically saying, I can't talk about that. So we'll see next week what Dave can't talk about. We'll also find out
what he can talk about.
the very small amount of things that he can talk about. But basically, Dave has the best hobby ever, and I'm totally jealous of him. I'm so excited he's coming back. So yeah, all right. So thank you folks for watching tomorrow, and we'll see you around, I suppose. See you later.